Today's presentation, we are going to talk about the introduction of the project, objective of the project, wind energy conversion system, mathematic modeling of the system, control techniques of the system. At the end, we are going to discuss about MATLAB simulation, and at the end, we are going to also discuss conclusion. Introduction. Next is objective. The main objective of this project is as follows: extract maximum energy from the wind by using TFIG wind turbine, improve power quality, active and reactive power control, improve the dynamic system and transfer stability, and prevent failure of wind energy system during asynchronization with the existing grid. Wind energy conversion system. A wind energy conversion system (WECS) uses wind energy to generate mechanical energy, which is then transferred to the electrical generator to generate electricity. Wind turbine generator can be permanent magnets, induction generator, synchronous generator, and so on. Wind energy from the wind turbine is transferred to the generator. These figures show the wind energy conversion systems. Um, the kinetic energy of the wind hits the aerodynamically designed blade of the wind turbine, which result into the rotation of the wind turbine. Sometimes the wind speed is not sufficient to rotate the blade of the wind turbine at that speed, where power generation is not possible. To increase the speed of the rotor shaft, a gearbox mechanism is required in some wind energy conversion system. The mechanical energy of the shaft is converted into the electrical energy by the use of the generator. The electrical generated energy is supplied to the connected grid. Wind turbines are classified into four types based on their overall characteristics as listed below. First is fixed speed wind turbine. Second is variable speed wind turbine. Third is doubly fed induction generator based wind turbine. And last is permanent magnet synchronous generator wind turbine. Mathematic modeling of the system. The wind turbine model is essentially a representation of the relationship between the mechanical power extracted from the turbine and the wind speed, and which is expressed as P wind is equal to 1 half rho A Cp lambda theta V cube. Here, rho is the air density, A is the swept area by wind turbine, Cp is the maximum power coefficient, lambda is the speed ratio, and V is the wind speed. Wind turbines with variable speed are built to operate their highest aerodynamic efficiency in the various kind of wind conditions. It is now feasible to continuously adjust the rotational speed of the wind turbine to the wind speed to variable speed operation. In this manner, the tip-speed ratio lambda is maintained constant at the maximum power coefficient, which is a predetermined value. A variable speed system, as opposed to the fixed speed system, maintain the generator torque relatively constant and adapt the generator speed to account for a variation in the wind. A variable speed wind turbine electrical system is a more complex than a fixed speed wind turbine. Now, tip speed ratio lambda is defined as the ratio between the speed of the blade tip and the wind speed, and it is expressed by lambda is equal to 2k by p into omega r divided by uh, v wind speed. Torque defined by the parameter like the staff motion of the rotatory mass of the wind turbine, gearbox, and machine shaft. Here, consider the transmission of the wind turbine to the machine shaft is the losses. Torque from the mechanical shaft Newton into meter is given by Tm is equal to K by 2 lambda rho pi r cube Cp lambda theta wind speed square. Mathematical modeling of DFIG is given by as follows. Vector of Vs alpha is equal to Rs into vector of Is alpha plus d by dt of vector of phi s alpha plus j into omega s vector of phi s alpha, where vector Vs alpha is equal to space vector of the stator voltage, phi s alpha is equal to space vector of stator flux, and vector Is alpha is equal to space vector of the stator current, and rotor voltage given by vector Vr alpha is equal to Ir into Ir alpha plus d by dt of vector phi r alpha plus j into omega s minus omega m into vector of phi s alpha, where vector Vr alpha is equal to space vector is a space vector of rotor, and vector Ir alpha is the space vector of rotor current, and vector phi r alpha is the space vector of the rotor flux, and here omega r is given by omega s minus omega m. The relationship between current and flux is given by vector phi ss is equal to ls vector iss plus ln into vector ir into s, and rotor flux vector phi rr is equal to lm vector isr plus lr into irr. Here L Lr is equal to rotor inductance, Ls is equal to stator inductance, and the formula expresses the coordinate of the stator and rotor. Note that here S and R suggest the space vector are as known as a stator reference system and rotor reference system. The electric power on the stator side and the rotor side are calculated as follows. PS is equal to d 3 by 2 PDS ITS plus VQS into IQS. PR is equal to 3 by 2 VDR IDR plus VQR and IQR. Here, reactive power Qs is equal to 3 by 2 Vqs Iqs minus Vds Ids, and reactive power for rotor is given by 3 by 2 Vqr Iqr minus Vdr and Iqr. This whole power, active and reactive power, is given in the TQ reference system. DFIG control. Some of the control techniques to control DFIG is given below. First is scalar approach. Second is vector control. Third is direct and indirect field oriented control. Fourth is rotor and stator flux control. Fifth is adaptive flux observer. There are many techniques which is used to control DFIG. Generator active and reactive power, amplitude, phase, and frequency of the torque that flows between the uh, rotor and stator can be changed by alternating the phase. For DFIG, grid side converter and rotor side converter is most popular for controlling. Grid side converter. The goal of the grid side converter is to control and maintain DC link voltage at the constant level regardless of the rotor power and to ensure that the rotor circuit operates with the unity power factor. This figure indicates the grid side converter. The condition of the DC link voltage always affects the how much power the grid side converter exports. The DC link voltage is monitored by the grid side controller and the grid side converter can export more real power to the if the DC link voltage increase by adjusting the load angle until the DC link voltage return to the nominal value. The DC link voltage will decrease if the grid side converter is exporting more power than the rotor side converter. The grid-connected converter features the base bidirectional switches in the construction. It has ability to switch between the DC and AC voltage and current as well as between DC and AC power or AC and DC voltage. An idle switch is frequently built with the antiparallel diodes and controlled semiconductor to enable current to flow in both directions. An insulated gate bipolar transistor or controlled semiconductor is used in this discussion. The grid-connected filter uses a minimum of three inductors to link the converter's output phase to the grid voltage. An LC capacitor or even numerous inductors should be employed in addition to each inductor when higher value of filter parameters are necessary. Rotor side converter. The rotor side converter is used to control and eliminate dot oscillation and improve the fault guide through operation capability. To maintain the torque of the generator, reactive power communicates between the stator and grid and rotor side converter with the filter to generate the three-phase voltage of varied amplitude and frequency. With rotor side converter, dV by dt filter is primarily intended to reduce the phase voltage in the machine rotor terminal from the converter. Figure shows the dV by dt filter. Here, inductance is intended to reduce the voltage drop and losses caused by the low frequency resistor, prevent the capable reflection. The filter typically consists of a typically two passive parts. For MATLAB simulation, we use 1.5 megawatt DFIG motors. The specification of doubly fed induction generator is as given below. The synchronous speed of the doubly fed induction generator is 1500 rpm, rated power is 1.5 megawatt, and all the parameters we can see in this table which we can implement it in MATLAB. Simulation detail. These four figures show the active and reactive power for stator and rotor. This output is taken at 1400 rpm. The synchronous speed of the machine is 1500 rpm. So this both output is taken at below synchronous speed. At first, no control action is initiated as the machine begins to run for rotor. The machine will start as an induction motor, draw electricity from the grid, and being controlled operation after 1 second when the speed is lower than the synchronous speed. After the specific oscillation, it will then function as a generator and stabilize at the one reference value. For stator, we can see that there is a more fluctuation from the starting to till the 1 second, and after 1 second it will stabilize at some point. The both figures show the DFIG active reactive output power at 1650 rpm, which is taken above the synchronous speed. because the machine speed is greater than synchronous rate, there is no control action is initiated when the machine starts operating. As an induction generator, at first it will power the grid and begin controlling operation a second later. After that, it will only function as a generator and following a certain oscillation and stabilize at the reference value of the output power. In the last conclusion, this project represents the modeling and simulation of DFIG. The MATLAB simulating software is used to carry out the whole simulation. A method for controlling the active and reactive power by using rotor side converter and grid side converter for wind power conversion system outputted with the DFIG and connected to the grid has been proposed. In future, by changing the reference parameter, we can get an ideal DFIG based wind energy conversion system. Thank you.